Welcome everybody back to continue lecture 7, sensitivity analysis. Now we're going to study if the changes in the constraint coefficient, if changes in AJ, one of the columns in constraint matrix change. The column J of the constraint matrix AJ change from AJ's to AJ prime, and that's what's going to happen. First, if AJ is a non-basic column, we need to calculate the new reduced cost. Okay, why the reduced cost? The reduced cost should be actually, again, will be CB transpose B inverse times AJ. So since AJ changed from AJ changed from AJ to AJ prime, so ZJ is going to change to ZJ prime. And this could be equals to omega transpose times AJ prime minus CJ. Okay? So this is what happened. And basically, we change also the CB transpose times YJ prime. So Y columns also change. So the current tableau, the Y column, since AJ changes as well. So Y column equals to B inverse times AJ, change to YJ prime B inverse times AJ prime. So this is straightforward and easy. Okay, if ZJ minus CJ maintain less than or equal to 0, this is fine. If not, we just entering this particular variable into the basis. So as AJ is non-basic column, it's fairly straightforward. The major changes will be the YJ change to YJ prime, and also ZJ change to ZJ prime, and the reduced cost also change. So we just need to double check if the ZJ minus CJ term, the reduced cost term, still maintain non-positive. If the AJ is a basic column who changes, then two conditions can be happening. First is loss of the basis. If this is the situation, of course, and this lecture contains several methods to correct this, but in reality, if that's the case, and it's better to resolve the linear program. Because using the method we discussed in the textbook is suitable for smaller problem, and it's a very tedious process. However, for the large problem, there is hard to implement at all. But we go through this a little bit and see what transpired to it. We look at this example, number 1. We have 3 variables, adding 2 slack. One is x4 and x5. Right hand side equals to 6 and 4. Okay, so this is optimal tableau. Notice all the ZJ minus CJ portion are negative or 0, and right hand side are all non-negative. So we know we have optimal tableau. The reason is all the right hand side, which is the current basic solution, are feasible. All the ZJ minus CJ is less than or equal to 0. We know all the due constraints are satisfied, so it's due feasible as well. So this is the current optimal tableau. Assuming A1, the first column changed from, what is the first column we have? From 1, 0, 1, negative 1, right here. 1, negative 1, first column, A1. From 1, negative 1 to 0, negative 1. See if we still maintain the basis. Okay? Since the current B inverse is 1, 1, 0, 1, where do I identify that? We already know that. Since x4 and x5 are slack variable, x4 and x5 are slack variable, so the B inverse will be residing on that. slack variable region. So this is a slack variable, and this is my negative omega vector. All right. So let's look at it here. So 1101 times 0, -1, I will have 0 and -1, okay? Right here. And also, since y1 changed from y1 originally, what is the y1 originally in the optimal tableau? This y1 is 1, 0, okay? Now change to 0, -1. 0, -1. Then we need to recalculate z1 minus c1, because z1 equal to cb transpose times y1 prom minus c1 equals to -2, 0 times the new y1 prom minus the cost coefficient for x1 equals to 2. Okay? So now y becomes a non-identity column, since originally x1 is the basic variable. So z1 minus c1 is not equal to 0. y1 and y5 are linearly dependent now. We lost our basis. So what we do is the current basis is lost. So what we do is using artificial variables added to our system, and then using the big M method, trying to driven out this artificial variable x6. All right. So what we do is we can actually show you example as a tableau. Once we're adding an x6, okay, as a basis right here, then we trying to get x6 out of the simplex tableau. All right. So make a identity. So therefore, I have get rid of x6. So x6 is going to leave the variable column. Okay, x6 is going to leave the basis. So after adding x6 into this column, we're going to make it identity so x6 can stay within basis. So this is a situation happen. In this case, we have what, x4, x3, and x2. Our candidate can be coming in as a basic solution. And this, most of the cases like this, you almost have the similar computational effort as to resolve the entire simplex tableau with a new AIJ. So this method, see here, you have 3 candidate actually x1, 2, 3, 4 all have positive zj minus cj term. So any of them can enter. Of course, x3 has the largest one. So next iteration, we will bring in x3. So it's too much effort. We usually just resolve the problem. I'll give you another example. If A1 changed from 101 to 36, and we can perform the similar situation. However, this is again is very time consuming as well. It's probably better just resolve the linear model. So we kind of understand if the constraint column, one of the constraint column change, meaning if the product has a new usage for our resources. So meaning if the technology change, if the production process change, and each one of the product you produce for this particular product use less or more of the resources you have. In this case, it creates a current constraint matrix column okay, constraint matrix column are changing, which means you change a production technology, you change the formula or production process in this case. Usually what we do is in this linear programming model, instead of we change the constraint matrix for this particular product, we virtually create a new product, because actually this product using different proportion of your constraint, your resources, I'm sorry, using a different proportion of your resources. So we're using create additional decision variable in your constraint and trying to see if this new product or the new project is worthwhile to replace the existing project or existing product. Everybody kind of understand what I'm trying to say? So what I'm trying to describe right here in industry and practical point of view, instead of changing the constraint coefficient column and trying to using sensitivities analysis to perform these maneuver, it's better to adding a new decision variable called xn+1, and you see if that particular project or product, depends on what type of application you're using, as a new decision variable, and put it into your simplex tableau. That's the next topic we're going to talk about. If we adding a new project or product into the linear programming model, how that's going to impact our current optimal solution. Okay, the slide actually, slide number 14, talk about if we adding a variable xn+1. Actually, the computation will be fairly easy. Since xn+1 is newly added, we're going to add, assuming it is a non-basic variable at this moment. So we're going to recalculate his y column after pivot, giving the original column, okay, original input column an+1. So you're adding another column into your tableau, and then you calculate what is the column at the current optimal tableau. Also, you can calculate the zn+1 minus cn+1, the reduced cost, using the newly calculated yn+1. Okay? So we adding this extra column into your table and see if the current tableau is optimal or not. If the zn+1 minus cn+1 is negative or non-positive, then there's no point to adding this product. If this product actually, new product or new project create a zn+1 minus cn+1 is positive, it is worthwhile to introduce this product. Okay, so if we still have the optimal feasible solution, if zn+1 minus cn+1 is non-positive, or else we can produce an extra iteration to entering xn+1. This is what I'm talking about for the previous situation. Instead of you changing the column for existing xk variables, especially when they are basic variable. And currently basic variable, meaning this particular product or project actually is active, was chosen to be produced certain optimal amount. In this case, if you want to change their cost coefficient due to a technology change or due to a production process change or engineering design change, okay, it is much easier just adding an extra column and treated this project as a new project and see if this new project, xn+1, is worthwhile to perform. If it is worthwhile, of course the xk will be driven out from the basis. Or otherwise, the old xk who originally changed, the old technology is still worthwhile to produce. still make it profitable. So this is my personal opinions and based on experience, and also is a technique we use in the industry and the practical sense. Instead of changing the cost coefficient, the constraint coefficient, it's better to adding a new column and see if the old column will be automatically get out of the basis.